Thank you. Thank you for the introduction, and welcome to my presentation. I'm very, very happy to be here today and to present you our work on edge computing and the relation between edge computing and the, I would say, post-Moore era that we are currently experiencing. I would like to start with summary of the, I would say, paradigm shift that we are currently experiencing in the software development, where we have this very, I would say, fundamental shift from how the programs are developed, where we had in the past software engineers that take data and rules, create programs, and then we get answers. Today we have data and we have answers. If I'm sitting in a self-driving car, I know the answer, I don't want to hit the wall, and I need someone to create rules that avoid hitting the wall, right? While sitting in a car, and we have a number of computers, supercomputers, clusters, edge nodes, doing the job for us and creating the rules. But the downside of this paradigm shift is that the systems that we are using are now time-sensitive, data-intensive, geographically distributed, and the worst thing is they are non-stationary. That means we learn a model of the environment, we learn a model of the world, and then something is changed. The data distribution is changed, and we have to do it again and again and again. And this results in the explosion of energy demands. And I think this picture shows it very nicely. I think it's bad, but the picture is nice. Yeah, cannot help myself. If you look at the picture, the red region means that the production of ICT will stay nearly the same. I mean, we will need almost the same energy, even though we have more devices. The yellow region shows something very interesting. The consumer devices, the end devices, are getting more and more and more efficient. They are tinier, they are more efficient, so they use even less energy in the future, and they will be using less energy. But there are two concerning developments. First, we put basically everything what we have in our data center in a cloud. So we have explosion of energy demands for the clouds and data centers and supercomputers in general, which is the green region, and another region is the blue region. So guess, if we put everything in a data center, we have to access it somehow, right? So we have explosion of energy demands for our networks, plus all the services that we are using all the time, like Netflix, they are so super convenient, streaming services, and the energy consumption for our networks is going to explode. So what I want to show you now, this is a video provided to me by my colleague Hannes Kaufmann at TU Wien, and they are developing multi-user virtual reality environment, which is super powerful. Means you might have 5 medical doctors at 5 different continents, and they think they are in the same room. They can jointly at least train to perform a surgery. Or you can use this application for fire brigades to exercise some dangerous operations, or in military purposes, gaming, I don't know, tourism. But why I'm showing you that, this lady, she's wearing a laptop on her backpack. Any idea why? I mean, it's not very fashionable. I would not do that. Yeah, actually, it's the latency issue. They have 15 sensors on their body, and they produce about 50 images per second on the glasses. Right, so I can have a wonderful data center. It doesn't help me much because the computation has to be done in a very close vicinity of the person wearing the glasses. And if it's not, they really get sick, and I'm not showing you that on this video, so we are continuing. Okay, so what happens now? We have so-called continuum of our computational devices that are necessary to perform the computation of, I would say, life-changing applications that we have nowadays, starting with vehicular networking, cyber-physical systems, virtual reality, personalized medicine. We heard also from Karen about the possibilities of personalized medicine and cancer treatment, robots. On top, we have massive data centers, abundance of resources that doesn't help us, so we have to use sometimes what we have in our environment, like routers and switches, and if they are not powerful enough, we install so-called micro data centers that do the work for us. So the beautiful landscape of data centers, so this is how a data center look like, I think, and I guess every one of you knows that. But we have now very heterogeneous data centers with different flavors and shapes. I know Microsoft is working on underwater data centers to get cooling for free, plus to have low latency because half of the world population is living in coastal areas. We have Huawei micro data centers that you can put into the corner of your office so you have your data in your office. Okay, I can tell you that. I call this is the first hop data center. I teach my students, for me, this is the first hop data center. It's a Raspberry Pi, but I can use it to do some computation, data staging. It's a very simple computation, but can help me to create messages that are worth to be transferred over network. We have highlighted your data centers. We have liquid cooling data centers. So data centers are more and more hyper-heterogeneous, and it's increasingly getting very difficult to execute applications in such continuum of very diverse data center infrastructures. And what we try to deploy applications on the computational continuum in a vertical way, but also in a horizontal way. So you can use, for example, swarm computing to utilize the continuum not only in a vertical way, but also in a horizontal way. And in particular, we look into new resilience strategies for edge data centers, because there are a lot of problems that cannot be solved using traditional methods. Why? If we talk about edge computing, we have extreme low latency, we have ad hoc networks, we have different type of failures, we have unstructured dynamic and heterogeneous architectures, and fault tolerance mechanisms that we know, like retry or checkpointing, they simply don't work in the area of edge computing because of super low latency, and we have lack of traditional support. We don't have fully duplicated electrical lines. We don't have diesel generators. So we have to devise new fault tolerance strategies, plus we have new type of failures that appear just in this type of systems, or very frequently in this type of systems. And here is an example that can show you the spatiotemporal dependencies in such systems. So if you assume we have server 2 and server 1 that are geographically distributed and they have the same power supply, so if power supply fails, they are going to fail concurrently, so this is the concurrent failure. If now server 2 gets overloaded, there is a policy that the data is distributed to server 1, so if server 2 fails at time point t, server 1 is failing at t plus 1, and this is also dependency in space and in time. And I have to tell you that the dependencies, such dependencies are not known in real system. We don't know them. They are not written anywhere. So the question is now, how do we deal with that? And the problem is now, if I'm deploying 2 replicas at server 1 and server 3, I want them not to fail at the same time. otherwise I nullify the effects of replicas. And this is why I tell you, okay, we are working on energy efficient systems. I want to minimize the number of replicas in my system. I don't want to use 5. I want to use 2 if possible, right? And how can we deal with that? Well, there are dependencies everywhere. And I guess every one of you can draw this graph here. This is the common knowledge of computer scientists. how the failures in a simple system depend. If you have power outage, everything fails, right? If you have operating system failures, so we have reduced availability, and so on and so on. So we can immediately draw such graph. If we observe the occurrence of such failures, we can collect the evidence. And over time, we can do the inference in both directions. We can say how probable is the power outage in certain system, but we can also say how often is availability affected by the power outage, right? So we can make assumptions and decisions about the system. So doing such graphs in a small system is easy, I would say, and it's common knowledge, but we have such dependencies in large-scale systems as well, data centers that consist of thousands of servers. And we performed analysis on the data of such data centers. We used data collected by Los Alamos National Laboratories that were provided for the public usage. And you can see the log files. So the 0 means node doesn't work, and 1 means it works again, and you have the timestamps. And if you analyze now the timestamps, you can see that time step of a stop time of a certain event is begin time, start time of another event. And this is how we connect failures in space and time and can analyze the dependencies. Again, we don't know why the node fails one after the other. Maybe there is some dependency in the workload, but they do. And if they do it very often, there is also the evidence that there is a real problem, so we can avoid, for example, deploying replicas on these two nodes. And we developed a system where you can learn such failure dependencies from a random architectures, random infrastructures. We use it for densely coupled data centers, but we also use it for the distribution of geographically, intelligent traffic lights, to learn how they depend on each other in a smart city. So what we have here, you have input, the network topology and the log files of the system, no matter which type of a system. Then you learn first the graph. So what we do here, we create such graphs in the first step. In the second step, we collect the evidence, so the conditional probability tables. And then in the next step, you can have your candidate deployment. Let's say I want to see how probable is that both servers are going to fail at the same time, right? And then you get the probability. And now you have the interface to your system administrator or to your operating system. We created interfaces with Kubernetes, where we can now try to deploy replicas on the servers that are not going to fail at the same time, or where the probability is very low to fail at the same time, right? So the next problem that we have that I also want to tell you about is geographically distributed machine learning. I know how many of you are using electrical vehicles? Anyone? Oh yeah, there are some of you. Wow, nice. Why are the others not using electrical vehicles? What is the main reason?
Because I work from home.
You work from home, okay. Other reasons? Costs, okay. Other reasons? Yes, that's also a good reason. What I also very often hear is they are just afraid that they run out of battery, that the battery is empty somewhere at the highway, right? Recharging intervals, oh, they are so, yeah. Nah, not that nice. So the reason, what we are doing here, we want to collect data from cars. All the data that car is so producing, like velocity, speed, fuel, start time, destination time, and so on, and try to optimize and route the people to the charging stations so that they don't have to wait. Difficult, right? So one way to do that is to collect data from the vehicles to create huge models. You know, also renewables depend on weather conditions, environmental conditions, so you cannot always produce power. So you have to match production of the electricity with the demand of the cars, which is also a big issue. You need machine learning here. So on the one hand, you have these big models that create model of the environment, how the power is produced. On the other hand, you have to collect data from the cars all the time You don't have enough bandwidth, so you have to use roadside units where we have some edge servers. So when the car is in the vicinity, you push all the data to the edge node, and you can create here a small model where you can do the inference in a very, I would say, convenient way. But the problem is that we suffer here of non-stationarity because everything changes all the time. Weather conditions changes all the time, road condition changes all the time. People just change direction for whatever reason, right? And then we have also insularity. Cars are not reachable all the time. They might be in tunnels, in rural areas, whatever. So the problem is now how to achieve accuracy of the analytics that we are used at data centers, core analytics, in such highly unreliable, geographically distributed environment, right? We want to have geographically distributed edge analytics with minimum communication overhead, with similar accuracy at core data analytics, where we suffer of insularity, non-stationarity, and intermittent connectivity. And we have generated a very, I would say, generic approach here. It is called Staleness control problem, where we speculate on the future developments and the exchange of messages. And I have to tell you here, we don't exchange data here, we exchange models that aggregate the data, which is way cheaper than sending raw data across data centers, cars, and users. So the Staleness control problem looks like that. Imagine you have two edge nodes that have received updates from all the cars in the vicinity, and now we send the updates so everyone has the same information, so there is no insularity anymore, right? Or we can say, we want to optimize message exchange, so we wait until we receive from one more edge node, but then we suffer here from low utility. Here we have high utility that drops down over time because of the age of information, right? Or we can say, we wait until we receive all updates from all edge nodes that exist. Then we have here extremely low utility, but here we have high utility. So you can guess what I'm trying to formulate here. We have to decide, we can model here, we can decide here, we want to optimize area under the curve, but everything what happens if the t+1 has to be modeled stochastically. So we try to learn the policy when and how to optimize message exchange to have the highest utility possible, but not flooding the networks with the messages. So you might wonder, okay, how is this related to post-Moore era? There is a lot of relation with that, and we have heard in many talks, many of us, basically everyone, is trying to deal with that, with the problems of the limitations of the architecture that we have. We heard from Karen yesterday that she's working on the networks and interconnection and optical networks. We have heard from Jeffrey also on new chiplets and neuromorphic architecture. You were also discussing about that, so I'm also working on this problem, and everyone has different solutions, and that's nice about that, right? So everyone is, or at least what I see, many of us are trying to develop new accelerators, and that's what I'm doing as well. But what is my idea and what is the direction that we are taking here? So our assumption is, in the last 50 years, we were working towards generalized architecture. So we basically had one architecture that everyone was using, right? But if you look at the computation and the demand of computation, it's highly diverse, right? If you look here, we have solving linear and partial differential equations that require high degree of precision and has also, I would say, high computational complexity. But here you have spiking neural networks with, I would say, medium precision required and medium computational complexity. And then we have random number generation. I would say low degree of precision. I don't care if it fails sometimes, but also a medium computational complexity. So what I believe it's going to happen, we might have different computational units. We already have right? That are specialized for different types of computation. And the things get complicated if you have it geographically distributed. Maybe you remember my example with virtual reality, right? We have a massive data center, then we have edge computer, then we have our glasses, and maybe we will have some implant in our body, I don't know. It's geographically distributed, maybe on different architecture. So the problem that is going to be here is that precious cycles that are used for computation are not used for communication between all those geographically distributed entities, right? So we have geographical distribution and more time is spent on communication. And that's where edge computing kicks in, right? I had already also very fruitful discussion on quantum computing with Pete, I remember. Here is one example how quantum computing can help us, representing the energy configuration of a single caffeine molecule at a single instant requires approximately 10 to the power of 48 bits in a classic computer. On a quantum machine, you can do it with 160 logical qubits. Try to beat that, okay? So there are specific problems and application where quantum computer might be a really, really good solution, but we have a lot of problems in doing that. So if I show you again my wonderful slide of a beautiful continuum that we can use in a vertical, also in horizontal way, one might think, okay, let's exchange certain units and put a quantum computer and we calculate the caffeine molecules here. But it's not that straightforward. So you have to do a lot of work around to make it work, to integrate a quantum computer in a classical architecture. So I see utilization of quantum machines in a computational landscape as another type of accelerator. It's another type of accelerator that you can use to perform specific execution of specific tasks that are meaningful. We are probably never going to do A plus B on a quantum machine, right? But molecular dynamics, maybe yes, because you can very well model the native 3D structure of the molecules on a quantum machine on this Bloch sphere, which is highly, geometrical modeling and a kind of analog computing on a very specific hardware. Currently, there are two problems that you have to solve if you want to execute your code on a quantum machine. First, you have to deal with non-determinism. That is something completely, I would say, not new, but not common to computer scientists. It's not that you just, do pre-processing, state preparation, circuit execution, and measurement, and do post-processing. No, you have to do it multiple times. A lot of times, because all those machines are very noisy. So you don't get the result, you get a distribution over results, right? So this is the first challenge. The another one is that you usually cannot map your classic code to the quantum machine in a one-to-one manner. So you have to try to map it and minimize the error. Right? So it's a kind of an iterative approach where you try to create a cost function that minimizes the error of mapping your piece of code to the quantum machine. Right? And there are already major algorithms that help us to do that. We have variational quantum linear solvers, and we have quantum eigenvalues that facilitate us to do the native 3D modeling of, in particular, molecular dynamics. And now if you look at this picture here, the question is now, at one end, we have the quantum machine. At the other end, our end application might be virtual reality or modeling of caffeine molecules, I don't know. But all the other work has to be done on this computing continuum somewhere. That means you are creating your accelerator, but your accelerator can be somewhere. It can be on your laptop, on the router between your laptop and the supercomputer, or all the way around, right? And we have done already some work and experimental evaluations in this area. You can see again this picture of workflow modeling tool from Eva Dillman, which is very helpful here because you have to decompose your applications into the pieces and code parts so that you can extract the portions of the code that can be executed on the quantum machine. So basically you have two parts, or maybe 3, 4, 5, some part of code goes on the CPU, GPU, TPU, whatever, and particular pieces of code go to the quantum machine. And now the another challenge is there are no two quantum machines in this world that are the same. Everyone is different. There is no architecture, there is no standard. It's a wild west of computing. It's really the wild west. So what you have to do, you have to access the resource catalog to get information how the qubits are interconnected, and based on that, you can create quantum circuit description and execute your code. And we did that. We executed and performed benchmarking of molecular dynamics application together with a team from Eva Dillman, together with University of Southern California. We did and used multiple machines provided to us by IBM. We have colleagues at Jülich, and we created a test bed to benchmark molecular dynamics application on a hybrid HPC environment where pieces of the code are executed on the quantum machine and other pieces of the code are executed on a classic machine. Why am I showing that? So I'm from Austria. I think if I say I'm from Austria, I think I guess this is the image you have in your head, right? Isn't it? I have to tell you that 99% of people in Austria never saw this movie. Okay, keep that in your mind. This is Austria too. This is the inside of a quantum machine. Or don't ask me about the details, I have no idea. I'm happy that it works. And it was a quantum machine a couple of years ago. My colleagues from AQT, which is a startup in Innsbruck, fit the quantum machine into the rack. So what you can have now, you can have quantum error correction, fault-tolerant performance that fits into the rack that can be installed in a data center, in an ordinary data center, which is cloud accessible, data center compatible, and they have also first demonstrations on how to use it in finance, in security, and for chemistry applications that we also did together with Eva Dillman. Austria is a very small country. It's comparable to the state of Maine in US, but these are the institutions working in quantum computing. So we have high density, very, very high density of universities, startups, companies working on all different aspects of quantum computing that you can find. So I think it's a good place to do this type of work. To conclude, we have a lot of challenges, I know, in the area. You don't have to be expert. We have to map this to that. So, which is a challenge. We have to map concepts like sequence loop condition to concepts like gate, transpilation, and circuit, which is not easy. But there are some first ideas. We have first benchmarks. How to do that, how to create hybrid environments and benefit from the quantum execution. I have also to admit, we don't have any speed up yet, but that's not the issue. We are creating here a telescope technology to be ready when the computers are there in the size and also with all the interconnection that we need to facilitate smooth execution. My last slide is always the same. Everything what I presented is the effort of my team. And I want to thank funding agencies in Austria and Europe for very generous support that I received to do my research. Thank you very much.
Thank you very much. Fantastic.